Okay, welcome to section 9.5, the binomial theorem. So this is from chapter 9. This is the same chapter that gave us sequences, but like I said, we're not doing induction, but we are doing the binomial theorem. So from that same section. And what do they want us to do? Just two ideas. Evaluate this nj. Now this looks like a fraction to some students when they see it. There's no line here. Either the line right there would be, if you ever see a line there, it was a typo. It's parentheses, there's a top number and a bottom number. It means something, which we'll get to its physical meaning, or it's one of its meanings. But it's written this way, but it's written this way on your calculator. So it's written this way in the book and with a J over it, but it's written this way and with, well, an R and on a calculator. And so we'll see some actual calculations of it. And then the binomial theorem itself is essentially following this pattern indefinitely. So what's this pattern? Well, a plus b to the 0 we know is 1. Everybody knows that. To the 0. Right? A plus b to the 1, well, it's just a plus b. A plus b squared, most of you have memorized this one a long time ago. It's a squared plus 2ab plus b squared. There's a whole bunch of patterns forming here. Notice how a goes from squared to a to the first to essentially a to the 0. So the pattern for the a's goes like this. 2, a to the 1, well, or better known as a, and a to the 0, just an invisible 1, I guess, there. So that's a pattern. There's another pattern for the b's. It's the opposite pattern. Now I'm taking a formula that you've known for quite some time probably, a plus b squared equals this, but I'm breaking it down into all of these components. What's the 1, 2, 1? Well, those are the coefficients. There's an invisible 1 in front of the a squared. There's an invisible 1 in front of the b squared. So there's coefficients. There's the pattern for the a's, pattern for the b's. And it turns out, with some predictability, I'm not going to say perfect predictability because the coefficients becomes a little mysterious at first. But with some predictability, we should know what a plus b cubed is. Now, this is not a formula for, people generally memorize outside of this section of the book. But it really is a continuation of these formulas here. What happens to the a's, the first term? It goes 3, 2, 1, 0. What happens to the b's? Well, there's 0 of them, there's 1 of them, there's 2, there's 3. And then the coefficients are 1, 3, 3, 1. And I'm going to say a starting at 3 and decreasing to 0 is a pretty easy formula to remember. B, starting with 0 b's in the first term, 1 in the second, 2 in the third, 3 in the fourth, is a pretty easy pattern. In other words, if I just look at the exponents on A are 3, 2, 1, 0. One of the first patterns you might have learned in your lifetime. And the pattern for B is even more familiar, 0, 1, 2, 3. I'm saying it's B to the 0, B to the 1, B to the 2, B to the 3. So these are pretty predictable. In other words, I think you'd guess what would happen if I add a plus b to the 4. B would go 0, 1, 2, 3, 4. A would start at 4 and the countdown. Okay, I think you got this pattern locked in. It's these patterns that need some explaining. Where did this 1, 2, 1 come from? Where did this 1, 3, 3, 1? And what would the coefficients of the a plus b to the 4 even be? Well, I'll go ahead and tell you. The coefficients for this one is 1, 4, 6, 4, 1. And we're going to find out where that comes from in a moment. But you might have predicted the 1, and you might have predicted the 4, but the 6, well, turns out it's this NCR that tells us what goes on up here. All right. I just said it. I don't think I ever gave it a name. I said it as NCR, and that's the way people sometimes say it, NCR or NCJ. And sometimes we say choose to give the C an actual word, and choose R, or in this case, N choose J, and you might hear me say that because I don't really have a way of reading it without the C or the word choose. All right, so we're given this. Let me find a hypothetical number, 5, 3 here. All right. So we're given a number here, a number there. This is what it might look like if we're just trying to, if we actually have numbers in there. All right. And now, what is that? It equals something. It equals some number. Well, this is the formula we use to calculate this. And I like to summarize it as the top factorial. And I should say the top number is always always greater than or equal to the bottom number. So the larger number will be here, or they'll be equal. And the smaller number will be there. Top factorial, the bottom factorial, and the difference factorial. Top factorial, bottom factorial, and the difference factorial, n minus j. So, what does that tell us this is going to be? It's going to be 5 factorial divided by 3 factorial. Those are visible. And then the invisible calculation is, well, I have to figure out what 5 minus 3 is. Of course, it's 2. So that's 5, 4, 3, 2, 1 divided by 3, 2, 1 times 2, 1. Things should cancel. The 3, 2, 1s cancel. The 2 cancels with the 4. And I get 10. 5 times 2 divided by 1. Yeah, I get 10. So 5C3 is 10 if I apply this rule or this formula here. And again, my summary, top factorial, bottom factorial, difference factorial. I think students have the greatest trouble with difference because they have to calculate it every time. But let's look at it. And by the way, I already showed you that, I already mentioned that your calculator has this button. Well, your calculator has a way of calculating this because I told you calculator way of doing it. So understand, you can do all of these with a calculator. And we're going to learn yet another way of calculating these. But the direct method is this. So running through these calculations, the top is 4, the bottom is 1. And the difference, 4 minus 1 is 3. So we could probably start it here. The top factorial, the bottom factorial, the difference factorial. Well, 4, 3, 2, 1 times, well, 1 factorial is just 1, and 3 factorial, 3, 2, 1 cancels with 3, 2, 1. Well, they didn't cancel. They actually multiplied it out. But I'm saying if you canceled, you just get 4 kind of directly. Well, or you could multiply it 24 over 6. This one we already did, top, bottom, difference. They chose to multiply them out, which is fine, but the numbers get kind of big if you do that. In other words, I much prefer you cancel, cancel, and then divide here if you're going to do it this way at all. But in any case, we get 10. And let's see if there's anything interesting. Nothing really too surprising on this one. The top, the bottom, the difference. They were a little more clever here. Do you see this little trick they did here? This time they didn't actually tell you what 9 factorial was. They said, you know what 9 factorial is? I know it's 9 times 8 times 7 times 6 times 5 ... but it's also 9 times 8 factorial. And if you can just replace 9 factorial with 9 times 8 factorial, you can cancel the entire 8 factorial that you had here. They chose to stop at 8 factorial because they knew there was an 8 factorial down there. And so they were kind of clever with that calculation, which is 9 any way you do it. Now they could have done it here, top factorial, bottom factorial, difference factorial. But they went ahead and used a calculator, and this is what I was saying. In the book, they'll write it as 35 over some 15 without a line there, with the parentheses. But on a calculator, it's 35C15. So 35C15, and it's a fairly large number, as you can see. So these numbers get very big when you get into, say, 2 digits on these numbers here. So they gave you 4, here they give you 4 formulas. I guess they're formulas. NC0, so let's put an actual number in there. Let's say 6C0. It's 1. Why is it 1? Well, if you actually ran through it, you get 6 factorial over 6 factorial over 0 factorial. And we said in a previous video that 0 factorial is 1. So if this is 1, I just have 6 factorial over itself. So the fraction gives me 1. How about this? N C1. Let's write it this way. N C1. Well, that's just going to be N every time. And with similar reasoning, I could reach it by doing this little formula. Let's do it with 6C1. So I know the answer is going to be 6, but how do I know that? Well, it's 6 factorial over 1 factorial. So far that doesn't look like 6, but the difference is 5 factorial. So we have 6, 5, 4, 3, 2, 1, but on the bottom, I'll ignore the 1 factorial because this is 1. I have 5 times 4 times 3 times 2 times 1. Well, all this 5, 4, 3, 2, 1 cancels, and I'm just left with 6, as I knew I would be, because if I put a 6 there, I get a 6 there. All right, n minus 1, well, again, if I had, let's say, 6C5, that would also just equal 6. That's essentially what this formula is saying. And Cn is 1. So they're giving us these formulas. Notice, well, maybe you'll notice that where these come from, but again, we'll understand this a little bit better when we move on a little more. Pascal's triangle is something you might have seen. I actually have it written somewhere else, but it turns out that this NCR button on our calculator, or this NCJ, is a way to calculate entries in Pascal's triangle. I actually have Pascal's triangle here numerically. And, well, this is my handwritten one. The book has, book has it. This is a very popular thing, by the way. I feel like I've said many times, don't Google something in particular because it's not something that people talk about outside of one of my videos. But you can certainly Google Pascal's triangle and get a lot of information out of it. So I have Pascal's triangle, and basically the way it starts is you start with a 1 here, and a 1 there and a 1 there, and you want to think of filling in a spot. Let me do it down here. I want to think of filling in a spot between this 1 and this 5, but down beneath it here. So when I fill in a spot right here, between those two, I add those values together. So this 1 plus that 5 is 6. If I want to fill in this space, it would be 5 plus 10, 15. 10 plus 10 is 20. And by doing this, I'm creating a triangle. Now, how about off to the side? I still want this triangle. Well, I like to think of there being an invisible 0 right here. So it's 1 plus nothing. And there's an invisible 0 off here. So there's 1 plus nothing. And if I think of it that way, I have an explanation even of how this thing starts. It starts with a parenthesis. I got to fill in with something. Well, I'm not adding. What am I adding? Well, sorry. Let's start with a 1. What am I adding to figure out what these two terms are? Well, I'm adding this 1 plus nothing. This 1 plus nothing. That explains kind of the top of this formula. But how about this? 1, 2, 1. Yeah, it's 1, 2, 1 because of what I'm adding to get there. Now, I actually superimposed this. Let me see if I can get it to move here. I superimposed this Pascal's triangle, the numbers version, on top of Pascal's triangle, the NCR version, to make a point here. And that is something I said a moment ago. We calculated this value. And I said, there's another reason why I know it's 10. I could just match it up to my Pascal's triangle. So what's the fourth entry? 1, 2, 3. What's the fourth entry here in this list of numbers? Well, the first one is 1, 5C0, but we kind of knew that from a rule we had earlier. 5C1 is 5, 5C2 must be 10. We haven't calculated that tonight, but must be because it matches up. And 5C3 is also 10. So what I'm saying is we calculated 5C3 not that long ago to be 10. And so how many ways do we have to do this now? We can match it up to its position in Pascal's triangle. We can calculate it with this formula, or we can use a calculator. All of those are legitimate ways to calculate some entries in Pascal's triangle, or some of these NCR values. All right. Now, if you're just asked to calculate something directly, like what is 5C3, you have enough information to do that. But the big part about Pascal's triangle is the fact that we can use Pascal's triangle to help us with the binomial theorem. I'll do that in another video because this one is getting a little long. So come back for 9.5 part 2.